Gravity doesn't exist. That's what more and more scientists are saying. Einstein, the greatest physicist of all time, had a revolutionary understanding of gravity. But in the end, could he have been wrong after all? In this video, we reveal the spectacular new findings that turn our entire understanding of gravitation on its head. So make sure you stick around until the end if you're ready for a physics identity crisis. A very warm welcome, everyone. Albert Einstein revolutionized our understanding of the universe with his theory of relativity. Through his famous formula E=mc², we know that mass and energy are two forms of the same thing. A small amount of mass can be converted into a huge amount of energy, since it is multiplied by the square of the speed of light. By the way, if you're enjoying it so far, feel free to subscribe to the channel. And if you've already subscribed, you can really help the video out by giving it a thumbs up. Thank you very much, everyone. Yes, NASA recently carried out a spectacular experiment that puts Einstein's understanding of gravity to the test. Together with the dark energy survey, they examined the relationship between gravity and the mysterious dark energy, and the results were truly astonishing.
Gravity holds things together. In the smaller areas of the cosmos, it is the dominant force. And by smaller areas, I mean regions of the cosmos down to galaxy groups. Our Milky Way, for example, is gravitationally bound to the Andromeda Galaxy, which is why the two-star islands are even moving toward each other and will merge into a giant galaxy in the distant future. But in the very large areas of the cosmos, gravity loses its dominance. This is where dark energy takes over. The cosmos has been expanding ever since the Big Bang, about 13.8 billion years ago. But even though the Big Bang happened so long ago, the expansion isn't slowing down. In fact, it's actually accelerating. Space is getting faster and bigger all the time. So there must be some mysterious force that keeps making it grow. Since no one knows what it could be, we call it dark energy. So far so good. Now we know that gravity dominates on small scales and dark energy dominates on large scales. Although sometimes I still feel like I'm expanding myself. There are many ideas about what this dark energy could actually be. A kind of energy field across time and space that exerts a repulsive pressure, like a kind of anti-gravity, something like that, but no one knows exactly and there is no concrete evidence anyway. This raises the suspicion that dark energy may not exist at all, but rather that there is something wrong with our theory of gravity. Some researchers actually believe that gravity behaves differently on large cosmic scales than it does on small ones. While it holds everything together here, on a larger scale it might even push things apart. Or perhaps it has changed over the course of the cosmos's evolution. Maybe it was stronger in the early days of the universe and gradually became weaker. A continuous decrease in the strength of gravity over the past few billion years would explain the increasing acceleration quite well, wouldn't it? Such alternative theories of gravity are very popular, and in the absence of evidence one way or the other, they could be just as true as the idea of dark energy, at least for now. The only drawback, perhaps, a gravity that varies over time would unfortunately contradict Albert Einstein's general theory of relativity. A research team from the Dark Energy Survey collaboration has now put this alternative theory of gravity to the test in a spectacular experiment. This should clarify once and for all the relationship between gravity and dark energy. They have conducted one of the most precise tests of Albert Einstein's general theory of relativity to date, looking at huge cosmic distances. We're talking about distances of up to 5 billion light years. By way of comparison, our Milky Way has a diameter of only 100,000 to 200,000 light years. On this gigantic scale, the researchers studied galaxies and measured subtle distortions caused by gravity as it warps space-time. Imagine space-time as a kind of invisible trampoline that is dented by the gravity of celestial bodies. It was precisely these space-time trampoline dents that the researchers were looking for. Space-time trampoline dent. Good word for Scrabble. The effect that the researchers took advantage of is called gravitational lensing. This effect is relatively strong for heavy and nearby objects, such as black holes within the galaxy. On the large cosmic scales of distant galaxies, it is rather weak, which is why it is referred to as weak gravitational lensing in this case. By locating these weak gravitational lenses, the Dark Energy Survey scientists were even able to determine the effects of gravity on a large scale in the past. Because as you surely know, every glance into space is a glance back in time. We see objects as they looked when the light set out on its journey. We therefore see galaxies billions of light years away as they were far, far in the past. Researchers examined almost 100 million galaxies at different distances for evidence that gravity fluctuated at some point in cosmic development. And what did they discover? Nothing. Not a single deviation. Gravity has been just as strong throughout the entire history of the universe. In fact, the galaxies studied, some of which are billions of years old, behave exactly as Einstein's theory predicts. So once again, Albert Einstein has been proven completely right. So once again, general relativity has come through unscathed. Now, some of you might be saying, that's so boring if they didn't discover anything at all. Not at all, because they did discover something. Namely, that alternative theories of gravity are probably incorrect and that dark energy probably exists. Because if gravity itself is not responsible for the accelerated expansion of the cosmos, then it must be the ominous dark energy. Which unfortunately leaves us with the question, what on earth is dark energy? And a few last doubts about Einstein's theory of gravity are still allowed. Researcher Agnes Ferté says there is still room to question Einstein's theory of gravity as measurements become more precise. We still have a lot to do before we are ready for Euclid and Roman. That's why it's important that we continue to collaborate with scientists around the world on this problem. By Euclid and Roman, she means two planned space telescopes that will bring us considerably closer to the answers to these big questions. The ESA's Euclid Space Telescope, which launched in 2023, is entirely dedicated to the search for dark energy. Like James Webb, Roman will be an infrared space telescope, but it will be designed more for viewing the very large cosmic scales, while James Webb is better suited to targeting individual objects. Roman will therefore be ideal for shedding more light on the connections between areas billions of light years apart. However, it will not be launched until 2026 at the earliest. There is yet another puzzle that has occupied physicists for decades. If Einstein is right and the speed of light is the absolute upper limit in the universe, then why does gravity seem to act instantaneously? Shouldn't it also take time to propagate? This question leads us to one of the most fascinating aspects of the theory of relativity. One of the most confusing aspects of gravity in any case is that it seems to act instantly. Or does the gravitational pull of the sun that holds the Earth in place also break away from us at the speed of light? To solve this mystery, we need to delve a little deeper into Einstein's physics. In his theory of relativity, Albert Einstein discovered that space and time are inseparable. Together, they form space-time, and gravity influences space-time. The heavier an object is, the more space-time, which we can imagine as a kind of grid for simplicity's sake, is curved. You too are currently influencing space-time with your weight. Of course, that doesn't mean you're overweight. Another important insight from Einstein was that there is a maximum speed in the cosmos. This is referred to as speed c. The theory of relativity states that the speed of light traveling through a vacuum never changes. At around 300,000 kilometers per second, light has the highest speed achievable in the universe. And that doesn't just apply to light, by the way. Even though people commonly refer to the speed of light, this actually applies to all other electromagnetic waves as well. What determines this maximum speed? That's a bit tricky, but I've tried to illustrate it in this professional diagram. A spaceship flying through the cosmos moves through space and time. The faster it moves through space, the slower time passes. You remember the concept of space-time. Now let's imagine a photon, a particle of light. Of course, it moves much faster than a spaceship, namely at the maximum speed c. This speed has such a massive influence on space-time that the time component is completely eliminated. Time slows down so much that it stands still. For light, in this sense, time does not exist. And that represents the maximum exploitation of the relationship between space and time. You can't go beyond the complete elimination of the time component, and that's why the maximum speed is reached exactly at this point. I can already see the question marks in your eyes. Maybe some of you are now saying, but why is the maximum speed exactly at this point? In principle, that's a philosophical question as to why the laws of nature are exactly the way they are. It is essentially the programming code of our reality, like the laws of the matrix that govern us. Feel free to write your ideas in the comments. Where do the laws of nature come from? What is the cause of the physical laws of our cosmos? A kind of matrix or something completely different? I would be very interested to hear what you think, and I will try to respond to as many comments as possible, I promise. But now back to gravity. So how does gravity behave in this interplay of speed, space, and time? Isaac Newton, the discoverer of gravity, who according to legend had an apple fall on his head, believed that this force spreads without any time delay. Albert Einstein, on the other hand, said in his theory of relativity that gravity could also only move at the speed of light. So what is true? Doesn't the sun's gravity affect us immediately? Would the sun disappear right now? Would its gravity disappear immediately, or would it take about 8 minutes for us to notice? That is the time it takes for light to travel from the sun to Earth. A research team from Columbia University launched a very clever experiment years ago to settle this question once and for all. And in doing so, they were helped by the heavyweight of our solar system, Jupiter. Jupiter is twice as massive as all the other planets in the solar system combined. So it really tips the scales. Is that already planetary fat shaming? And this is what the researchers' experiment looked like. As Jupiter passed through the field of view, the researchers used several interconnected telescopes to observe the light from a quasar, the active, energy-rich center of a distant galaxy. The gravitational force emanating from Jupiter deflected the light from this quasar ever so slightly. They used Jupiter as a gravitational lens. From this, the scientists were then able to calculate the speed at which gravity travels. So, a method that is as simple as it is ingenious. The result? Gravity does not act instantaneously. It propagates at the speed of light. This was later confirmed by the first measurements of gravitational waves. Gravitational waves are a kind of vibration in space-time that occur when two massive objects collide. When two black holes merge, for example, the fabric of space-time begins to wobble. This wobble was successfully detected for the first time in September 2015 by scientists from the LIGO collaboration, almost 100 years after Albert Einstein predicted it. Gravitational waves are only possible if gravity propagates at the speed of light. According to Newtonian physics, which some scientists still adhered to at the time, such a wave would be inconceivable because gravity would reach the Earth immediately. So long story short, gravity moves as fast as light, and although this has long been disputed, it can now be considered proven. But there are still a few follow-up questions that come up. For example, if that's the case, why can't light escape from a black hole? But gravity can. However, this is based on a misconception about black holes. A black hole doesn't emit gravity from its interior. Rather, the black hole itself is the gravitational field. In other words, gravity doesn't have to leave the black hole at all. The black hole itself is a frozen gravitational field. Gravity can be static, while gravitational waves travel at the speed of light. After this detour into the speed of gravity and light, I couldn't help but think of the movie Interstellar. It presented the idea that there is an even more powerful, faster force in the universe: love. Even the curvature of space-time cannot stop it. And so here's a nice quote for you, which supposedly, one must always be careful, comes from Albert Einstein. Gravity cannot be held responsible for people falling in love. How on earth can you explain such an important phenomenon as first love using the tools of physics? Put your hand on a hot stove for a minute and it feels like an hour. Sit with this great girl for an hour and it feels like a minute. That's relativity.
The speed of gravity leads us to an even more profound topic: time itself. Scientists now believe that, with the help of gravitational waves, they can actually look back to the very beginning of time. They want to make the Big Bang itself visible. This revolutionary idea could change our understanding of the entire cosmos.
One thing is clear: time is the rarest resource in the universe. No matter how rich you are, you can't buy much more time. And even if we humans eventually overcome our mortality through technology, that doesn't change the fact that time is still limited. Because eventually even the universe will die.
And that's why physicists have long been searching for an explanation of what time actually is. But that's not so easy to say.
And so, before we continue, let's play a little game. Write me in the comments how you would define time. What is time? I'm super excited to hear your attempts, and we'll take the time to respond as much as possible, I promise.
Very fundamentally, you can simply think of time as a causal chain that describes the sequence of events. If I nudge a domino, it triggers a causal chain reaction, and the entirety of these individual causal effects. That's what you could call time. But don't get too excited just yet, folks. It's not that simple, as we know since Einstein. In special relativity, time is considered part of a four-dimensional space-time continuum that can be deformed.
And influenced by gravity, gravity not only affects space, it also distorts time and leads to what is colloquially referred to as time travel. If you spend 5 minutes next to a black hole like Gargantua from Interstellar and then return to Earth, you will notice that many years have passed here. So if time is part of the four-dimensional space-time continuum, then it must exist in some way, right?
And not just a simple sequence in a causal chain. But if time really exists physically, then where is it? Then, like everything else, it should somehow be anchored at the subatomic level. Everything in this room here can be traced back to the smallest structures on the quantum level. You are just a special arrangement of quarks. Of course, you are the most beautiful collection of quarks I have ever seen. But a subatomic particle of time does not seem to exist. At least we haven't discovered it yet.
We can measure time with great precision, but there is also no evidence that it works differently at the subatomic level than it does in the macrocosm. Most theories about the nature of time are based on mathematical models and observations in the macrocosm, but they have not yet been confirmed at the subatomic level.
So overall, we can say that time is obviously somehow there. But we have no idea what it really is. And that's despite the fact that it plays such a significant role in the cosmos, because all cosmological developments take place on a timescale. The Big Bang, for example, which according to prevailing opinion is how the universe came into existence in the first place, happened at a certain point in time about 13.8 billion years ago. If that was the beginning of space, it must also have been the beginning of space-time. And how fascinating would it be if we could look back that far? Now, some of you smart Alecs are going to object. Every look into space is a look back in time. Yes, that's true. Our eyes are, in principle, time machines.
We see things as they appeared when the light set out on its journey. The Andromeda Galaxy, for example, is 2.5 million light years away, so we see it as it appeared 2.5 million years ago. We see the Sun as it appeared just under 8 minutes ago, and so on and so forth. Unfortunately, however, the very early stages of space are hidden from our view. It was only when the cosmos had cooled down sufficiently, around 380,000 years after the Big Bang, that electrons and atomic nuclei were able to combine to form complete atoms. At that moment, light was no longer absorbed.
Instead, the now electrically neutral matter could pass through unhindered. In other words, the cosmos became transparent, and up to this point we can look back and see a gigantic, all-encompassing basin.
Cosmic background radiation. It is not possible to see beyond this, at least in the optical range, and this is where some scientists come in who say that we can look back to the beginning of time itself. Deepan Garg, a doctoral student involved in the research, says we cannot see the early universe directly, but perhaps we can see it indirectly by looking at how gravitational waves from that time influenced matter and radiation.
Gravitational waves are disturbances in spacetime triggered by the gravity of celestial bodies. The heavier the objects, the more pronounced the distortions in spacetime. For example, when black holes or neutron stars, unimaginably dense objects, collide, spacetime begins to wobble noticeably, and clever scientists on Earth can measure this with very expensive instruments. And the researchers' idea is as follows. What if we trace back the gravitational waves from the very early cosmos and
thereby glean information about the beginning of everything? The Big Bang was obviously an event that released an enormous amount of energy and must have caused space-time to vibrate considerably. However, the Big Bang happened quite a few days ago, which makes it somewhat difficult to detect the very early gravitational waves. Our technology is currently limited to detecting gravitational waves in the range of collisions between stellar masses, black holes, and neutron stars.
Primordial Big Bang gravitational waves? Not a trace. But instead, researchers have now developed a revolutionary method, specifically in the field of plasma physics. It has nothing to do with donating blood plasma, which, by the way, earned me a lot of money back when I was a poor student. As temperature increases, substances usually transition from solid to liquid, and then to gaseous states one after the other.
If the temperature is increased even further, plasma is created. That is why it is also called the fourth state of matter. Researchers have now used the propagation of electromagnetic waves through plasma as a simulation for gravitational waves in the universe and have developed a series of equations that describe what to look for when gravitational waves move through stars and gas in the depths of space. Or as Deepan Garg puts it, we basically applied the plasma wave machinery to a gravitational wave problem. This is an ingenious method of using terrestrial research methods to find out more about the elusive cosmic phenomenon of gravitational waves, and indeed, the researchers have made a very interesting discovery. According to their findings, the propagation of gravitational waves through matter generates a detectable signal. For example, changes in the light produced by stars or giant gas clouds in the space between stars. These signals can reveal gravitational waves that are currently beyond our detection capabilities. With this method, we have the key to an indirect glimpse back in time to the Big Bang, and we can learn all sorts of things from gravitational waves.
Since gravitational waves are generated by the acceleration of masses, they can, for example, provide us with information about the movement of matter and radiation in the early universe. How did the elements come into being? How did the first stars and galaxies form? They can also tell us how the expansion of the universe has changed over time, thereby ending an eternal dispute about the Hubble constant, i.e. the rate at which the cosmos is growing. And primordial gravitational waves can also help us better understand the nature of dark energy and dark matter, which together make up about 95% of the energy in the universe.
And about which we still have virtually no clue. So it seems that everywhere in the cosmos there are invisible timestamps from the time after the Big Bang scattered around, which we could read using the new method inspired by plasma physics. And in doing so, we might be able to answer the biggest questions of all. So who says science isn't exciting? So the researchers have discovered that these weak gravitational waves generate a signal that we can read. Now someone just has to actually do it so that we can truly catch a glimpse of the very beginning of time. I hope you're all gravity experts now. If you don't want to miss any more breakthroughs in research, remember to subscribe to the channel now, and don't forget to give the video a thumbs up so we can hit 5,000 likes. I would really appreciate that. And speaking of mysterious discoveries, NASA has just found something absolutely incredible inside the moon. A gigantic anomaly that calls into question everything we think we know about our satellite. This discovery could change the future of humanity and trigger a true space race to the moon's south pole. To find out everything about this spectacular lunar anomaly, be sure to click on the video shown at the top right. It's really exciting.
And below on the right, you'll find another video about science and space. Otherwise, I'd say see you in the next video. Take care, everyone.